So today we will talk about something that is very important. So we have a graph here, and on the y-axis it's pressure. It's pressure, and on the x-axis is volume. And we have we talked about the systolic and the diastolic. It's basically when the heart is pumping. So when the heart is squeezed, is on the systolic, and when the heart is getting more blood, is the diastolic. Okay. So okay, we have the end-diastolic, which is when it's almost beginning is the systolic. So we are increasing the volume, and so the pressure increasing, and then you cannot put more volume, so we start to put more and more pressure, something like that. Okay. And that's the ED, the end diastolic pressure volume relationship. The end pressure volume, and that's a relationship. Okay, so we have our left ventricle over here. Our left ventricle, say like this. Okay, and we're filling it with blood. So here the volume is 0, then begins to rise, and the pressure begins to rise. Okay, and here the pressure is normal. Now we begin to put more and more volume. We tuck everything here, and then the pressure starts to rise exponentially, right? And preload is basically the wall stress, or it's the left. It's the left ventricle. It's the left ventricle wall stress, or just LVWS. Okay, left ventricle wall stress. And we have a very famous person, which is called Laplace, and he was studying spheres, right? He was studying spheres, and he told, all right, this is a sphere. Okay, and he told that if we do a sagittal view, right, a sagittal cut, he told that the wall stress is equal to the volume. Oh, sorry. The wall stress was the pressure multiplied by the radius divided by 2W. Okay. So the radius is, let me do it a little bigger so that we can see it, right? So we have here two circles, right? Two concentric circles. And this is a zoomed version, right? So the radius is from the origin to this circle over here, okay? So that's radius. And the wall thickness is from here to here. That's the wall thickness, or just W. So that is W2. And the pressure, we know that the pressure is force, right, per area. So it's a force here going over a certain area. And the blood is inside here, okay? So that's the wall. That's the wall stress. Okay, so the wall thickness doesn't change too much, right? Because the heart doesn't change, right? And we have that our R total is going to be our radius. Our radius plus our W, which is the wall thickness. And we know the volume, right? And we have a relationship between volume and radius. This means that the volume is proportional to the radius. And we can change this proportional by an equal, and then you put a constant over here. Okay, so I know that V is equal to what? Is equal to 4/3 of pi, a constant, okay, times R cubed, or as we were saying, right? R cubed, okay? So I wanted to know R. R then is going to be 3 times V divided by 4 times pi, right? And all of this, the square root, the cubic root, right? So that's R, and we can plug it in on our equation. So we get that P, we get that P is equal to, wall stress, that's equal to P, pressure, times R, which is square root or cubic root of 3V over 4 pi, right? Divided by 2W. So let's do an example, right? So we have pressure. We have pressure. We have volume. we have the radius, we have the wall thickness, and we have the total radius, right? Okay. So let's say we begin with a 10 millimeter of mercury, a pressure, which in this case is millimeter of mercury. Our pressure is 10, okay. And the volume is 3/4 of pi times r cube. Well, in this case, over up here, we did the graph. So around 10 millimeters of mercury is going to be 125 milliliters. That's pretty normal. And over 15 is going to be around 150 milliliters. Also is very normal. Okay. So down here, we can plug in these values. So our pressure is 10, our volume is 125 milliliters. 25, okay. Our R. So volume is 4. It's equal to 4 or better. R, that's equal to 3 pi. 3 times the volume over 4 times pi divided by square root, cubic root. Boy, it's complicated. So if we do our calculations, it's 3 times 125, which gives us 375. And then we divide this times 4 times pi. And that gives us 29.8. Okay. Then we're going to take the cube root. Or we can just raise it to the 1/3, which is 3.1. Okay. So our R 3.1. So then we put R is 3.1. Wall thickness. The wall thickness is around 1 centimeter. 1 centimeter. And our total will be 4 times 1. 4.1. Okay. Let's do the same thing, but now with 50. Oh. Let's change up a bit the colors. And our total is 4.1, right? And so it was 10. Now we're doing it with 15. So our volume is going to change. It's 150. And now we will do the same calculation, which was 3 times 150, which is 450 divided by 4 pi, 4 times pi, which gives us 35, and then we raise it to the 1/3, to the 1/3, and gives us 3.29. That's 3.3, right? So we raised in 0.2 centimeters. Our wall thickness continues the same, right? And the total is 3.3 plus 1, which is 4.3. So you see in a 5 millimeter of mercury increase, we increase 25 milliliters, 0.2 centimeters. The W here, we take it as a constant, and the total will change accordingly, right? And here on the wall stress, we can know the wall stress, which is pressure 10 times 3.1, which is 31, divided by 2. That's around 15. And the other was 33 divided by 2, which is around 17. Something like that. So we can, and the is going to be pressure is Pascal times R is centimeter. And actually it's meter times meter. And W is also meter. So cancel out Pascal. This is pressure, preload. Wall stress is pressure, right? And by here we can see where we're P times, here we can see that the wall thickness is a constant. Volume is a number, right? And we take the cubic root, so it's negligible. So what changed what has the most power in changing the wall stress is pressure. And we're going to see what pressure does on our heart.